Assalamualaikum and greetings. My name is Muhammad Safwan bin ANUARI. My MATRICS number is 192074. The title of my bachelor project is Design and Simulation of Inline Turbine for Green Energy Power Generation. Large-scale hydropower plant has been widely used to generate electricity. However, hydropower technologies have not been developed too much in the small-scale or pico hydropower plant. In this modern era, large-scale hydropower application seems to be less preferred. Thus, the necessity of a small-scale or pico hydropower plant should be implemented. Pico hydropower technologies have been noticed as the best substitution to generate electricity in rural areas. The Inline turbine in the water distribution networks is a helpful energy harvesting method of pico hydropower technology. Why? Firstly, IHT depends on flow rates, velocity, and pressure difference in the pipe. Second, IHT working principle is the same as the conventional hydro turbine. Next, IHT design is compact and straightforward. It's also capable of converting even a small amount of energy in the pipe into electricity. And lastly, it is adapted to the current era and produce clean electrical energy. In the present day, the supply of energy generation, especially in rural areas, is a severe issue. The peak hydropower technology applied in the water distribution network provides excess hydraulic energy. The excess hydraulic energy in the pipeline of water distribution network can be used as the water head to produce electrical power, because extra hydraulic energy with enormous pressure is produced by the continuous fluid flow in the pipeline. The objective of this study are to redesign an hydro turbine for the water pipeline system, and to investigate the torque and output power of different blades number versus rotational speed of the inline turbine using Safwan 2021 R2. The geometrical parameters of the proposed design of the inline turbine are shown in the table below. This 3D design consists of several components, which are runner blades, shaft, and hydroelectric generator. For the 2D design, the several designs in this section were used as the geometrical design in the compositional analysis to investigate objective 2. The simulation model can be regarded as symmetric. The 2D design of the blade was built to reduce the compression time. The steady mesh technique was employed throughout the numerical simulation to allow the mesh motion between stationary and rotating zone. The turbulent model used in this simulation is a K omega shear stress transport SST model. For the grid generation of the turbine model, the unstructured triangle mesh was employed in both stationary and rotating zone. The phase sizing was used around the rotating zone, while the edge sizing was assigned around the turbine blade wall. The prism layer was applied to all the rotating zone walls to resolve the boundary layer. Using the inflation tool in ANSYS mesh software, the mesh network around the rotating zone is modified around the turbine blades. This is the quality of the mesh around the 6-blade turbine element. Figure A shows the mesh around the turbine, and Figure B shows the prism layer around the turbine blade. A mesh independent test has been carried out to verify the grid independence of the numerical solution. 8 sets of machine schemes were tested. The graph shows the dependence of torque output on the number of elements. This is the solver setting of solution method setup used in the current study. For the verification of the method used in the study, the simulation model of the inline turbine was performed with 2 different blades. The comparison study with previously research by Ma et al. 2018 was done with the same number of blades 6 and 12 and rotation speed of 10, 15, 20, 25, 30, and 35 RPM. Based on the both graph, the trend line of the torque output for both studies decreases as the rotational speed increases. The graph of the output torque produced were the same for both current and previous studies. Therefore, the numerical simulation may be proceeded further to investigate the best number of blades of the proposed design that will produce the highest torque and output power. Firstly, the result of the study is a torque analysis of different blade numbers. Based on the bar chart on the right, the blade number of 4 shows the highest output torque at 3 different rotational speed compared to other blades number. The highest output torque for the blade number of 4 was 17.56 Nm. In contrast, less output torque was produced for the higher number of blades more than 4. The pressure contest of turbine with blade number of 2, 4, and 6 have the most significant effects on the turbine performance. From figure of 4 blades number, it can be seen that the major portion of the flow hit the concave side of the blade for 3 different rotational speed. However, in the turbine of 2 blade number, it might not have enough capacity to capture the hydraulic potential in the pipe due to the insufficient blade number. Thus, most of the flow hits the major part of the concave side of 4-blade turbine, and since this turbine has more bladed than 2-bladed turbines, it creates a higher pressure difference. The higher pressure difference between the concave and convex sides result in higher torque output. For the 6-blade turbine, most of the flow in the pipe hits the convex sides, which causes this side will not under maximum pressure. Thus, when the major part of the flow hits the convex side, it will reduce the positive torque generation. Secondly, the result of the study is the torque analysis at different rotational speed. Based on the graph, it can be seen that each of the turbine blades perform differently at different rotational speed. The torque output shows the highest torque generation at 10 RPM for 4-bladed. Based on the figure, it can be seen that a major portion of the flow hits the concave side of 2, 4, and 6 turbine blades, which result in the higher torque production of the turbine. Similarly, the same phenomenon occurs for the turbine rotates at 20 and 30 RPM. This is 20, this is 30. Okay. From the figure, it can be seen that the minor portion of the flow hits the turbine blades of 8, 10, and 12. It shows that the pipe flow does not pass through the blade with the flow diverge near the pipe wall, which results in less torque production. Finally, the result of the study is the investigation of output power. The highest output power was obtained by investigating the optimal number of turbine blades. According to the graph on the right, the highest output power generated by turbine was 53.86 watt at angular velocity of 3.1416 radians per second. This optimal number of blades of turbine to achieve the result was 4-bladed and it produced the highest torque output. This is the simulation demonstration of the 4-bladed number at 10, 20, and 30 RPM. In conclusion, the inline handle turbine for the N300 part 9 cm was proposed, and the design was withdrawn with the best dimension based on the previous study data. Secondly, increasing the number of inline handle turbine blades up to 4 blades improves the torque output and shows the great performance, which can reduce the fabrication cost of this type of turbine for the future application in the water pipeline system in Malaysia, rather than fabricating a turbine of more blades number with a poor performance which consequently leads to high fabrication costs. Thirdly, turbines with a number of blades of more than 4 reduce the positive torque generation due to the low pressure difference between concave and convex sides of the blade and inadequate impact of the fluid flow on the blades. And lastly, the highest output power of the inline turbine was between 18 watt to 54 watt at 30 RPM. That is enough to light up the electrical appliances. That's all from me. Thank you.